Okay, so let's see where we stand. You're working on PS11, which is due Monday. Tomorrow I'll release the final assignment, which is PS12. It'll be due a week from Tuesday. And then we have finals week, and our exam is the last day of finals week, which is Wednesday, May 2nd. So the last lecture we'll do a review, and we'll be scheduling a session on Wednesday, reading day, so there are no exams on Wednesday before finals week. Andrew's going to do a session where he'll go over a sample final, answer questions about that. Maybe we can even arrange to videotape it. Don't mind being taped.
Sure.
But we'll have announcements about that. Any questions or problems about anything? Yes?
Regarding the assignment quiz, one of them is PS8. It's formatted as a quiz. If you could take the quiz, there's no questions to take. And so I actually got thinking that since I can't take the quiz, there's no questions. Apparently I guess it stayed in and it timed out something after like 6,000 minutes. And so I did the quiz, got 0 out of 0. And currently it shows my regrade score as 0 out of 100. I mean 0 out of 0 because the regrades are 0. But I was trying to regrade an assignment, and I've done this by messaging through campus messaging.
All right, let me stop you there. Let's talk about that offline. After class, we'll figure that out. Yes?
On PS11, could you talk a bit more about how to deal with tests that will fail, sometimes pass sometimes?
Okay, if you got tests that fail sometimes and pass sometimes, that indicates to me that the issue has to do with timing. It has to do with multi-threading. And those are notoriously hard to figure out. Your debugging strategy, you've basically got to be very analytical about your code. You've got to, first of all, you'll know which half of your code it's in, right? Whether it's on the sending side or the receiving side, and they're like different programs, really. You've just got to realize that all these methods can be called at any time on different threads. And just think what would be happening if 2 threads are executing at the same time, and look for issues there. It's really frustrating if you can't reliably reproduce the error, and that's the nature of multi-threading, unfortunately. Any other questions? Yes?
Are there any very common errors that we should be looking out for? Like in terms of multi-threading problems?
Well, perhaps. And I've got a few things I want to talk about in a minute, so maybe that'll jog some more questions. One other thing is that I released the grades yesterday for the PS9. I forgot about the regrade thing, so I'll put up a regrade deal so you can ask for regrade, because that was based on tests. But the rest of the assignments, PS10, 11, and 12, you have the grading test in advance. So we shouldn't have that issue there. Well, let me just talk briefly about string sockets, because that's what you're working on. Okay, so I'm doing this for 2 reasons. One is you're implementing string sockets this week, and PS12 are going to be using string sockets, so it pays to be familiar with them. One thing you're not implementing this week, but you'll use next week, is string socket listener. It's completely analogous to TCP listeners. Remember that TCP listener is at the heart of the server. You start a TCP listener, and it waits for requests for socket connections to come. And when it gets a request, it establishes a socket connection. String socket listener is something I wrote, which listens for connection requests, and when a connection is made, it establishes a string socket connection. So that's where string sockets will come from, ultimately. You won't need to create them directly in PS12. You'll use a string socket listener for that purpose. Okay, but that's not an issue this week. That's the issue next week. And as you must know by now, string sockets, the way to think about them is it's a wrapper around the socket. So the string socket encapsulates the socket, and it exists just so the user can think in terms of strings instead of in terms of bytes. So instead of saying, please send this array of bytes, you say, please send this string. Instead of saying, please receive some bytes, you say, please receive a complete line, or receive some number of bytes and convert it to a string. So you're implementing the constructor. When you do the constructor is called with a socket and an encoding. What's the encoding for? What is an encoding? Yeah.
It says how to view the bytes in order to convert it to characters.
Right. So it's a encoding tells you how to convert from bytes to characters and back, or from characters to bytes and back. So the encoding that's commonly used and that we're using is UTF-8, which is a variable length encoding. Some characters go to 1 byte, others go to more bytes. But the encoding controls all that. So you're just being passed UTF-8. All right, on the sending side, there's this begin send method. So once the string socket is up and running, begin send can be called at any point. And to call begin send, you pass a string you want to send, and you pass a callback of this type, and a payload, which is an arbitrary object. And the contract is that the string sockets will send your string out completely, and after it knows that every last character has been sent successfully, then it calls the callback, passing the payload as a parameter. Okay? And actually, it calls the callback, the payload is the second parameter. The first parameter would be true if the send succeeded, otherwise it'll be false. Now, how could the send fail? In what circumstances could a send fail? How would you know it had failed? Yeah?
The socket closed before the whole message could go through.
Right. So if you're trying to send the bytes of the string and the socket, the other end of the socket closes, you'll find out. And so there's no point in continuing trying to send the bytes. At that point, you just call the callback and say that you failed. Okay. Begin send. Your string sockets are supposed to be thread safe. That means that you could have multiple threads simultaneously calling begin send, which implies that the code you write for begin send had better be thread safe. For example, let's suppose that in your begin send method you're saving the string and the payload into a queue or something. You'd better be doing that in a thread safe way, because there could be 2 begin sends going at the same time, both trying to manipulate a queue or a list or something. And if you're not, you don't have a lock controlling that, then you could occasionally get a problem, program crash. So just be aware, multiple send requests come in at the same time. I want to draw a picture here. Erase this. Okay, let's draw a picture of this is a string socket. It contains within it a socket, and you can think of that socket as having a connection off somewhere on the internet. So this is the socket down which you can send bytes. This is the socket is something down which you can send bytes. We're not going to worry about receiving in this picture. You can have multiple begin send requests coming in at the same time. They can come in at any point. Okay, common mistake number 1. You get a begin send, you receive a string to send, and so immediately you call begin send on the underlying socket. So let's say this request comes in, you take the string, convert it to bytes, and call begin send on that thing. Why is that a mistake? Yeah?
Could you send like multiple of them at the same time?
Yeah, what you have to ask yourself is, okay, so if what we're doing when a send request comes in is that we convert the string to bytes and we call the socket to help start sending the bytes, What happens when this request comes in? We call the socket and tell it, okay, send those bytes. This request comes in. We tell the socket to start sending bytes. So what happens if the socket is not thread safe? The underlying socket is not thread safe. So if you start telling it to send, you tell it, send these bytes, send these bytes, send these bytes, send these bytes all at the same time, what's going to happen? The bytes are going to get mixed up. So suppose that the strings we're trying to send are big, long messages. Say they're like a megabyte long each. Okay? So the first guy comes in and says, send this, converts it to a byte array and says, send this byte array. Well, you can't send a megabyte at once. When you send something, what's going to happen is you're going to say, send this array. It's going to send part of it and tell you, I sent 4,096 bytes or something. And so you say, okay, try again sending the rest. Try again sending the rest. If you have 5 simultaneously attempts calling begin send on the underlying socket, the bytes in the various strings are just going to get in or leave on this connection. The remote receiver is going to get back a jumble of bytes, some from one string, some from another. You can only be sending one string out of the socket at a time. So you can't do something as simple as receive string to send, convert it to bytes, call begin send. You've got to write your socket so that it receives this information about what needs to be sent and saves it and only works on sending one string at a time. So even though you might have 5 strings that want to be sent, you're going to take one, send it completely, and call the callback. Then get the next string that you saved, send it completely, and then call the callback. And sending completely may take multiple calls of begin send on the underlying socket because it might not send all the bytes in one call. Okay? So if you haven't thought of that, it's not surprising that sometimes tests pass and sometimes they don't. It's just going to depend on how frequently, whether these begin sends all actually come at the same time. I mean, if the test case just calls begin send once, it's not going to matter. But when you get to the test cases that are calling begin send on the string socket from separate threads simultaneously, chaos is going to ensue. Okay? So that's a very important thing to know. You need some sort of data structure to keep track of what strings are waiting to be sent. Now, what do you have to keep track of besides the strings waiting to be sent? Yeah?
What order they need to be sent in?
Okay, they need to be sent in some order. And if you use locking, basically, if the code that adds, the code that's adding the string to be sent to some data structure, if that's protected with locks, then you are going to be getting, only one begin send is going to get through at a time. So you want to, you can serve the strings in that order. But what else do you need to remember besides the strings that need to be sent and the order in which they need to be sent? Yeah.
Who we're sending them to? Like what ports we're sending them out to?
You don't have, the underlying socket worries about that. You don't have to keep track of the port. It's always, yeah.
The ones that have been sent?
No, you don't need to remember the ones that have been sent. Yeah, but think about the information that's coming into the string socket begin send method. Yeah.
The callbacks and what order they were in?
Right, you've got to keep track not just of the strings that you're supposed to send, you've got to keep track of the callbacks you're supposed to call when the sends have completed, and also the payloads. So for every call to the string sockets begin send, those are 3 things you need to keep track of. So when the string finally finishes, you can call the callback and pass the payload along. What about this strategy? Let's say we have our string socket here, a call to begin send comes in, and we set a lock. And we don't release that lock until the string has been successfully sent. So if some other begin send comes along at the same time, it's just going to have to wait until this string, the sending has completed. Until the first string has been completely dealt with. Then we'll deal with the next one. What do you think of that solution? Right, it's slow. You have no idea how long it'll take this string right here to be sent. It might take seconds, who knows? Maybe the wireless will, fade out for a minute, for a few seconds. And while we're doing this operation of sending the bytes out, which may take a very long time, these incoming begin sends are all blocking. And finally, when the send is finished, the next one gets its turn. The rest are still blocking. You need to design this so it doesn't block for long. These incoming begin sends should only block for as long enough as it takes the information to be remembered. You shouldn't block until the entire send operation is done, because it's an unbounded amount of time it may take to send the bytes. You just don't know. So a call to begin send on the string socket should return practically immediately. So it's asynchronous. Okay? Now, could I use these pictures for the receive side? What do you think? Do these issues happen on the receive side?
Yes.
Yeah. You can get multiple calls to begin receive coming in on the string socket, but the underlying socket can only be working on receiving, dealing with one string at a time. It's going to read some bytes, and when it gets a complete line, it's going to call a callback, the next callback in the queue, and then read some more bytes till it gets a complete line, do the next callback in the queue, and so on. So it's sort of the same structure on the receiving side. When you're told to begin receiving a string, you're going to need to store the callback in the payload to use when the string has been read. And you certainly don't want 5 simultaneous threads, each one trying to read bytes from the same socket, because again, your bytes will get mixed up between the strings you're trying to read. Okay? If you look at my simple chat server, it had to deal with these same issues. There weren't callbacks, but there were similar things, similar shared state. So the first thing you need to do is understand the simple chat server. It won't do just to copy the code of the simple chat server and hope for the best, though. You really need to understand how it works. So that would be time well spent, is figuring out the simple chat server and asking questions about it. Okay? So, are there any questions I can answer now about the sum you're working on? Yeah?
So can you clarify more about the difference between those two pictures? Because I don't understand how it is more efficient to block or lock the sending process than locking the whole request, like begin receive.
Okay. Suppose everyone in the front row here wants to tell me to begin, they want to give me a string and a callback and a payload. And they say, wait till the string has been read, call the callback. So what I want to have happen is, they all say begin send, and I immediately say, okay, I've begun sending. They immediately can go back to whatever they want to do. They're not blocked. All right, now I go to work. I take whoever got in first, I'll send their string, and that may take a few hours, and when it's done, I call his callback. And then I start sending the other string, and then when it's done, I call the callback. In the meantime, their threads aren't blocked. Now, if I take the strategy that as soon as he gets through with a send request, I make everyone else wait while I send all the bytes out and call the callback. How long are they going to have to wait? Who knows? It depends on the sending, how long the sending takes. So I don't want the amount of time anyone has to wait dependent on the time it takes to send.
So follow-up question. So you take and save the request in a queue, you said.
Mm-hmm.
But how do you guarantee that the first request will be replied first?
Well, first request will be first in the queue. Right? They all try to call begin send. I'm using synchronization. There's a lock. But the lock exists only long enough for me to get his callback and payload and string and add it to my queue. Then I return. Then I get the next one in line. I add him to the queue. I add him to the queue, and so on. So very, very quickly, I have 6 items on the queue. In the meantime, there's another thread inside that's starting to send bytes out. So it gets the first thing off the queue and starts working on sending it. And when it's done, it calls the callback, and it goes to the next element on the queue.
Oh, I meant to, so what if the second in the list, in the queue, queue's callback is called before the first ones in the queue.
Well, that won't happen because you, well, actually it doesn't matter. If two people about the same time ask for a string, or ask to send a string, they'll go out in some order, right? Whoever happens to be lucky enough to get in first, their string will be sent first. And then the callback will happen.
Is that always a guaranteed thing? Because,
Yeah.
so the socket always works on one.
Yeah, the socket's just a stream of, the underlying socket's just a stream of bytes. You got to be sure that there's just one thread that's trying to send bytes out the socket. If you've got multiple threads trying to simultaneously send bytes down the socket, they'll just get mixed up. Yes?
So the amount of work that you do, not front row,
Mhm.
is still the same in both scenarios, though.
Yes, same for me.
Right. It's
But
just
your
that
experience-
we get freed up to then keep.
Your
people.
experience is different, right?
Okay. Okay.
When you call begin send, you don't have to worry, am I going to be blocked for an hour waiting for everyone before me to have all their strings in? You just have to say, okay, I'm going to be blocked for a millisecond while my information is getting put on the queue. Yeah, you're guaranteed to not block for a long time. Yeah.
So if we were to say use a queue, like when you send stuff to the socket, it gets put into a queue, and then later in like another locked section, you also like take and then that's where you send the bytes out of the queue.
Mhm.
Wouldn't having access to the queue in both different locks potentially cause hazards?
Well, you've got to use the same lock. The code that's writing to the queue and the code that's reading from the queue need to be protected by the same lock.
Okay.
And if you've got some code here and some code here, that's all locked with the same lock. Only one thread at a time can be in either critical section.
Sure.
Code is executing here, there won't be another thread executing here.
Wouldn't that mean that if you have like it's taking, say an hour to send somebody stuff, then this section up here can't be accessed by the other lock, the section that takes stuff and adds it to the queue.
You don't hold the lock while you're sending. All you do is hold the lock long enough to read something off the queue.
Oh, okay.
Then you start sending. You can release the lock because now you're done with the queue. Now you can start sending. Okay? Any other questions? Okay, it's going to be a different experience because this is multi-threading, no way around it. And you've got to, if you're used to debugging by, if your only way you have of finding mistakes is by stepping through the debugger, that may not work this time. You've got to be able to analyze your code, to sort of look at it, and find out where there are race conditions, where you made a mistake with the multi-threading. And it's really the first time you've done that, so expect it to take some time. Really good to just talk to your partner, kick ideas back and forth, and start early. If you haven't started by now, it's not early, but start now. Okay, so this is receiving. We've already talked about that. There's just the other side is receiving. So you say, please receive a string, and you've got to call the callback. Okay. Thing to remember is this optional parameter right here is the number of bytes. So if this is, say, 100, what you're saying is please read the next 100 bytes and convert that to a string and give it back to me. Yeah?
I had a question about that implementation. So if you receive, say, like 20 bytes in it, and it gives you length equals like 4.
Mm-hmm.
Once you're done reading those 4 bytes in, what do you do with the additional?
You need to save them.
You save them?
Yeah, for the next thing, next request that
Okay.
comes in. You can't drop bytes on the floor.
Okay.
If at any point, that's going to happen when you're asked to read a complete line, so you read up to a new line. You don't know how long the line's going to be, so you read some bytes, say read 4,000 bytes or whatever, you read another 4,000, eventually you see a new line. But you're going to have leftover bytes. You've got to save them in the state of your string socket.
So what happens if you use so you have like a callback queue, and you don't have any more callbacks, but you have more bytes to be.
You save them. Again, so if you run out of, if your queue becomes empty, you stop sending because there's nothing to send. You stop receiving because you got nothing to do. Then when the queue becomes non-empty again, you start up your sending thread. Okay? But if there are any leftover bytes, you got to save them, you know, in expectation you're going to get another request to send or another request to receive in this case. Okay? Let me tell you another thing you might be tempted to do. And that is always send and receive 1 byte at a time. Because if you only send and receive 1 byte at a time, you don't have to worry about having extra bytes left over, right? You just read as much as you need and you stop reading. What would be the problem of always dealing with 1 byte? Read 1 byte, send 1 byte down the socket. It could be extremely slow. The way it works is you're going to end up creating a thread for each byte. It's going to be really slow. It's going to time out the tests. So don't do that again. Okay, question, yeah?
Would you suggest we stick to that 1024 size as our how much to send at a time?
I never know. I always use a multiple of 2 just because, a power of 2.
Yeah.
You know, 1024, 4096, 2056, one of those. I have no idea what's optimal. A few thousand bytes. Okay. Okay. So these are operations that are already implemented, but they're shutdown and close. What shutdown does is it closes it, but first it gives the socket some time to finish up what it's doing. Close, if you just call close directly, if it's in the middle of sending some bytes, they're never sent. So it's best to close it by calling shutdown, which shuts down this one. Okay, now, you'll be doing PS12. So you need to know a little bit about HTTP. So let me remind you what PS12 is going to be. You're going to take your working, hopefully working service, your boggle service, either from PS9 or PS10, whichever you like best, whichever works best. And you're going to take your hopefully working string socket. Or if your string socket's not working, you can use the ss.dll I gave you. You can use my implementation of string socket. But anyway, you're going to take some string socket implementation, some service implementation. You're going to modify the service implementation by essentially taking out the stuff that Visual Studio, that the project is doing for you automatically. So currently in your service, you don't have to worry about listening for socket connection requests and creating sockets and reading the bytes and turning them into strings and taking the URL and figuring out which service method to call and then figuring out what response to send out. We're going to X all that out. So you'll be left with your service methods in your database. And you in PS12, you've got to provide that missing part now. And at the heart of that missing part will be a string socket listener. And it will listen for connection requests. When it gets it, it'll create a string socket, and then you've got to do okay, so the string socket's connected. What will your code have to do? A request has come in and you got a string socket that's talking to a remote client. What are you going to have to do to make your service work? No takers? Well, what's happening automatically? What is your service doing now? What happens in your service now when it gets a request? Yeah?
It waits for your request and listens to it.
Okay, so it waits for lines of text to come over the socket. What does it do with the information that comes over the socket? What information? Yeah?
It passes it back to a delegate or a callback.
Well, okay, now we're standing outside the... Okay, so you'll have a callback. Your callback says a line of text has arrived. Okay? What do you do with that line of text? You've got to somehow extract from that line of text the information you need to make the service work. And so you can't begin to do this until you see what text is going to come across the wire. And that's what the first part of this is. You've got to know a little bit about HTTP, the Hypertext Transfer Protocol, which is the heart of the web. So suppose a remote client does a GET request like that. HTTP:// and so on. So that's to get information about a game. Okay? This is what's actually sent across the socket connection. Actually 4 lines. There's a blank last line. You can't see here. There'll be the word GET, because that's the kind of request. There'll be the URL. You know, the protocol is stripped off. And there'll be the version of HTTP that's being used. The next line will tell you, well, I guess the protocol and the host name are stripped off. So this is actually the host name. And it tells you that it wants a response in terms of JSON. Then there's a blank line which tells you there's nothing more. Okay, that's what your program will be seeing. You'll be making calls to your string socket to get lines back. The first call will give you that first line. The second call will give you the next line, and so on. You don't have to worry about bytes. You're just getting a line at a time. Okay? What do you do with that information? You get that first line. What are you going to do? What on this first line matters? Yeah?
The request, the game name, and...
Okay. So that's important. We got to know, is this a get, a push, a put, whatever, a delete? This isn't very interesting, at least up to here. You know what that's going to be. So what's interesting is this. That tells you it's a GET request on games. And the URL says what to do. I mean, the API says what to do. So you're going to have to read this line and say it's a GET on games. It's going to have to extract this as the game ID. And then it's going to have to say, okay, I know that when I've got this URL and I've got that game ID, I'm supposed to call this service method. So your code will just call the service method, which you've already written. The service method will return a JSON object, which is the response, and then you've got to generate the HTTP response and send that out. So you're just providing a connection between the information that comes in this form and the information that goes out. So your service methods you don't have to mess with. You just have to provide the mechanism that deals with the HTTP protocol now. Fortunately, it's not very hard. So this shows what I was just talking about. We've got the type of the request, you get the URL, we've got the parameter embedded, you've got to be able to pull that out. There can be more headers, depends what client you're using. And the headers can come in any, they're case insensitive, they can come in any order. There's always a blank line that tells you there are no more headers. And very important, every line ends with /r/n. If you don't put carriage return, if you just put new line, there'll be problems. So make sure your lines terminate with carriage return new line. Okay, what about that second line? What do we do with it? That host line. Yeah?
I'm going to guess nothing.
Nothing. We don't care. Our service doesn't care. Maybe if you're a web browser, you might have something to do with that. I don't care the name of the IP address of the client. I don't really care. What about that accept? It says I like a response in JSON. Yeah?
Is that the format to send the information back in?
Yeah, it's the format we're supposed to send information back in, but what if it says something like application/XML? Too bad, I only know how to send things back in JSON. So you can ignore that too. You're going to send something back in JSON whether it wants it or not. Right? A better service might look at that and format the response according to the desires of the remote client. But we're not going to change that part. So really, once you say it's a GET request, you just need to look at the first line. But you have to read the rest to get them out of the... You need to keep reading lines until you've read that blank line. Otherwise, the It'll screw up the next request that comes in, but you don't have to parse it. Okay, so that's one example. What about this one here? This is a post request, so it's trying to, what does this post do? Join a game maybe? I forget what this one does. You're trying to join a game. Okay? What bits are important up there? Bits of text, that's what I mean. What matters and what can you ignore? Does the post matter? Yeah, you need to know it's a post request. What about this URL? The games and the G0 are important. What about this, HTTP 1.1? Again, if we were a serious browser, a serious server, we would notice, okay, is this 1.1 or 1.2 or 1.0, and that would change what we expect to see down here. We're just going to hope everything works. And we're ignoring most headers anyway. Okay, that doesn't matter. That doesn't matter. That's saying the incoming thing is in terms of JSON. It better be in terms of JSON, because that's all we're going to be equipped to deal with. This is important, though. That 79 is important. Why is the 79 important? What does the 79 mean, even? Yeah?
Does that relate to all of the user token and time limit stuff?
But the 79 is the number of bytes in the number of bytes that follow this blank line right here. So that's where you use that second version of your begin receive. So you'd say, give me a line, give me a line, give me a line, until you hit the blank line. And then you would ask for, okay, read 79 bytes and give me that string back. So you get the 79 bytes that we convert to a string, the string socket will hand it to you. Then you've got to parse that as JSON and turn it into an object and call the service method and get the response back from the service method and then send the response out. So again, you're just pulling this apart. Extracting information, ignoring most of the headers, paying real close attention to the method that's being used and to the URL that tells you which service is being requested. Okay? And this just summarizes that. So the new line happens here. There's not a new line here. So the new line always comes after the last header. Okay, the blank line, I mean. It's got to be carriage return new line. Blank line, and then comes the message body, the request body. There's no blank line here. You've got to generate responses. So suppose you're going to send back, you got to send back this JSON object. You've got some object you want to send back. So what you do is the service says that when you successfully deal with this request, you put a 201 up there, let's say. So the first line needs to look like that. The next line, then there's got to be a header. One header is going to say, yeah, I'm giving you back JSON. Another header is going to say, there's 52 bytes after the blank line. So the client is able to read the 52 bytes and convert that into an object. So that's what an HTTP response looks like. It's just lines of text. Okay? So what I've told you here is what an HTTP request looks like, in a very stripped down fashion. It's just a few lines of text that you've got to pick information out of, and what a response looks like. It's just a few lines of text in which you've got to put information. So fundamentally, it's not a very difficult thing. How would you characterize a program that can read these lines of text, decompose them enough to make a service call method, take the response from the service call, and then generate the response? How complicated a program is that? When have you written a program that reads a few lines of text, extracts some information, and writes a few lines of text? Probably before, presumably before you were in 3500. I mean, it's fundamentally a very simple thing. It's just string operations. Okay? So don't be freaked out by it. Now, I'm going to next go point by point through we're going to walk through what the server is going to have to do, what the service has to do from the time it first starts receiving your information on the socket, and when it's done sending stuff out. So let's take a break and we'll look at that. take a round trip through a service call. Okay, so your service must first of all be able to receive connection requests and establish socket connections with the remote client. So what is it that makes that possible? How will you do that? Yeah.
TCP listener.
TCP listener, if you were going to use sockets, which it says. But we want to establish string socket connections, so we should use a string socket listener. Okay? So at the heart, your main method for your server is going to start a string socket listener that's going to listen for socket connection requests and create string sockets when a request comes in. Okay. So you've got some method that's been called that says, here's a string socket to use. And you look at the socket and you read the first line off. Okay? What's it going to take to read the first line out of a socket?
String socket,
String socket dot
begin receive.
begin receive. All right, so you call string socket dot begin receive, and then you're done. And when that string has been read, then the callback will be called. So you'll have a callback that deals with that first line. All right. So now the callback has been called with that return line. Now you got to examine the first line and determine, is this a put, a get, a delete? How do you do that? How do you decide from the first line which service method you're supposed to call? That's the first line of the HTTP request. Yeah.
Like the first word.
First word is important. That's the put, the get. What else is important?
Also like the extension like games or users.
Right. So part of the URL is important. So you sort of got to take that first line apart and get some important bits out. How do you do that? That sounds like a use case for what? Regular expressions. If you're still afraid of regular expressions, then it becomes a substring problem. String search, substring. But regular expressions would be a neat way to do that. Okay, that first line also is going to contain, perhaps, in the URL itself, are going to be parameters that are needed for the service method, like that G0 in the example. Or it may be you're getting a status and you've got to read the optional parameters, if any, out of that first line. They would, the query string of the URL, question mark part. Okay, how would you pull those bits out? Yeah, it's still a regular expression problem. Now the regular expression will pull strings out for you. Some of them you may need to convert to a different type. It may be that you have to, I don't know if you need to do that or not. If you need to, say the service method expects an int and you've got a string, you'd have to parse that into an int. I don't believe that'll happen. Okay? All right, so now you've decided what service method to call, and you've gotten some of the parameters that are needed out of the first line. So now we've got to at least read the rest of the lines through the blank line, just to get them out of the string socket, even if we throw them away. But maybe we're expecting a JSON object as well. So what we're going to have to do at that point is read the header lines one at a time, expecting to see a content link header, and if there is one, we're going to pull out the content link from it. That's where you will have to parse to an int. So what will that code look like? Realign, extract content link if possible, and you keep doing that until you see a blank line. Shouldn't be a mystery.
Regular expressions.
You can use a regular expression to see if it's a content link header and to pull the value out. Otherwise, you're just calling begin receive repeatedly. Give me the next line, give me the next line, give me the next line. And you wouldn't be doing it in a loop, though. You'd be doing it via callback. So read a line. When you got it, call this callback. Okay? If there was a content link header, let's say it's 79. That means you've got to read the next 79 bytes after the blank line how are you going to read, and turn it into a string? So how are you going to do that? How do you read a specified number of bytes? Yeah. Right. You use begin, receive again, but you use the version that takes the number of bytes to read. That's why that method is there. It's just for this very thing. Okay? Now you've got bytes. Well, really, begin, receive to give you a string back. So you've got string. You've got to convert that into JSON. You got to convert that to a C# object. So you've got JSON in string form. You've got to parse that into a C# object. How do you do that? Got an idea?
JSON convert.deserialize object.
Right. JSON convert.deserialize object. Now what that does is it takes the string form of JSON and converts it into a dynamic object that's represented internally. I don't know, maybe it's an expando object. But your service methods don't expect expando objects. You've declared, say, a user type that has properties and a game type that has properties. I don't know, for your service methods, you've declared little classes that have the properties that the incoming objects and the outgoing objects are supposed to have. So, fortunately, there's a way to deal with that. Let's say you're expecting, your service method expects a person object. So you can just say JSON convert.deserialize. If you give person as a, between those angle brackets, it'll convert the incoming string, if it can, into a person object. As opposed to, you don't have to say dynamic. It will literally be a person object, which is what your method needs. So assuming the properties of the incoming JSON object match up with the properties you declared in the person, which they will if you're following the protocol, that'll happen for you. You can get the person object out that way. So that's pretty easy. Okay? Now you got to call the service method. How do you do that? Come now. I just asked you, how do you call a method? Yeah?
You have to have some object of the interface that you're going to then call method on?
Yeah. Yeah. So I hadn't thought about that issue. But basically, you got a method you need to call. And you've extracted all the parameters you need. So you just call the method. You do what, it's just a method call. So you got the existing service method, you just call it. Okay? So your service method is just like it was in PS9, PS10. Now, in your service methods, when you decide what the status code, the return status code is supposed to be, you're calling some method like set status code. Now that part won't work anymore. So what I recommend that you do is for each of your service methods, you add an additional out parameter called status code. And so you return the status code by, what you do to set the status code, you just set that out parameter to contain the status code you want the response to have. That's the simplest way to deal with it. Okay? So you've gotten that status code, and you've got to send out the first line of the response. So now you're calling begin send. Now you're generating the HTTP response, and you've got to look at the definition of what it looks like. You create what the first line of the response looks like, and you call it. You've got to put a content type header in. That's application JSON. That's just string socket.begin send. Okay? There may be that what you've got to send back also includes, in the response body, a serialized JSON object. So what are you going to do? Your service method returned a person object, let's say. How do you convert it to JSON? To a JSON string. Yeah. Now it's JSON convert.serialize object. That turns it into a string, and then you use begin send to send that string out. Before you send it out, though, you've got to determine how many bytes it contains, because that's got to go in a header. You've got to put a content linked header that says how many bytes follow the blank line. And there's a method called encoding.getByteCount. So you've got an encoding that you're using, UTF-8. So you call encoding, you call get byte count, and it'll tell you how many bytes it'll take to encode the string. So that's the value of the content length. You send a blank line, that's begin send. If there's a string, a JSON string you got to send, now you send it out to the blank line. Okay? What could go wrong? What errors could occur? Right. You could get a request that you look at the URL and it's not part of the API. Someone just sent you garbage. What should you do if, so you're going to have a conditional that says, okay, if the URL was this and the method was this, call this service method. Else, call this service method. Else if. What's the else going to be? What do you do if none of the above? If no valid service method is named? Yeah?
Give a status code of 400 or something.
Yeah, that's like a 404 or something. Some 400 status code. Basically, the client made a mistake. What if the client leaves out the game number from the URL? That's the client's mistake. That's some kind of 400 response code. Okay? The JSON the client sent didn't parse. 400 something. So, yeah.
The 400, like for the unit test, which 400 is for that request, or do you have one particular in mind?
If the API specifies, that's the only thing I have in mind. If the API is silent, which I think it is, any type of 400, just use the 400 code that seems to make the most sense for the error. So basically, you're going to be catching exceptions. If an exception occurs that was unexpected, just respond with a 400 response code. Okay? Other things that could go wrong are your code fails. Presumably that won't happen. Assuming that the request was correct, your code shouldn't fail, but maybe it will. So what do you do if there's an unhandled exception in your server after you've ruled out any client errors? Yeah?
You send back a 500 code?
That's what 500 codes are for, internal server error. So you don't want to just crash the server. Right? So catch exceptions. If it's a client's fault, some sort of 400 response code. If it's the server's fault, some kind of 500 response code. Okay? Okay, you got to do this for minutes. You could be being simultaneously requests. Maybe what I do for, imagine if someone fired up 20 Visual Studios, all on different machines, and are simultaneously running tests against your poor service. So it's getting 20 simultaneous requests to do, 20 simultaneous requests to do things. How are you going to make sure that doesn't result in chaos? Yeah?
Making sure it handles multi-threading, locking it.
Okay. Yeah, it's a matter of dealing with multi-threading, but here's the good news. As long as your service methods are written either to use a database, which takes care of multi-threading requests, or if you're using your PS9 version, as long as you've got locks around all your service method code, there's absolutely nothing you have to do for number 13. The string sockets are already multi-threaded. They're thread safe. You did it right. Database is thread safe. So that's the good news. It'll just work. So no work, nothing needed, no extra effort needed for 13. So fundamentally, there's a lot of detail to keep track of, but it's like just do this, do this, do this, do this, do this. All the complicated code is already written in your service method. The only change I recommend you make in your service method is add an out parameter to each that's used to return the status code. So it should be, it's a good final assignment because as long as you got a grasp on what you're supposed to do, it's straightforward. Okay? So before I move on to my final topic, are there any questions I can answer about this? I know it's hard to think about PS12. We haven't started PS11.
Could we also modify the set status method that we were provided to get it that way?
I'm a little worried about the set status method. Okay, so the issue is This is what I think happens. No. I know what's going to happen. You just, okay, what's your set status method going to do?
Like store it somewhere?
Store it in a variable?
Yeah.
Then, so you're creating a new instance variable.
Oh, yeah.
Now you got to worry about simultaneous requests. What if you got 2 requests at the same time trying to set that variable?
Yeah, mess up.
Leave that out. Just do it via an out.
Okay.
And then you don't have to worry about synchronization. I'll tell you what you can do if you really want to do it that way, though.
Yeah.
Is that each time you get a request, each time you get a string socket, create a new instance and, you know, call the methods on that instance. Then it would have its own copy of the instance variables. You can make it work. You just got to think about it. Any other questions? Yeah.
The dictionary.txt that we scan in, do we have to walk around that, or should that been something we put in the database?
Well, I wouldn't put the dictionary in the database. What you should do with the dictionary is, when the service starts, before it's dealing with any requests, you should read that dictionary and store it into a set. And then store that set as a read-only static variable, or as a const. And then it's thread safe. No one's trying to write the set, and you could have multiple threads trying to read it simultaneously. So that's how you deal with the dictionary. Okay. Anything else? Okay. Well, I have just the amount of time I need to return to my favorite topic, which is the C#, Java, C++, what have you, memory model. And we've talked about this before. I just like to return to it time and again and add to it to deal with things that we didn't talk about the first time. So, this is my sermon every time I talk about the memory model. You'll do yourself a real favor if you gain a good understanding of what your program is doing in memory when it runs. It'll help you write better programs. It'll help you understand bugs. It'll help you when you study systems. It pays off all the time. And I'm just talking about stack and heap diagrams. So what we're talking about is the data structure that your program manipulates as it is running. All right? It's got to use memory. This is how it uses memory. Things we want to figure out is, how does your program look up variables that it needs to? How are value and reference types treated differently? How are value and reference parameters treated differently? How is inheritance supported? How are interfaces supported? So we've talked about some of that stuff before, but not all of it. I'm not going to show you every last detail, just the basic idea. And like I say, we've seen a lot of this before. So let's just start with basic value types. So we've got this method, main, that calls that method f. So the fundamental thing is, when a method is called like main, it gets a stack frame. Now, this stuff over here is not really in the runtime model. It's just for us to look at so we can tell the difference. This is the stack frame on the runtime stack that's going to hold the value of C and X. And that's what's actually there at runtime. So what's going to happen when main runs? Int x equals 3. It's not hard stuff. What will change about my memory? We'll store 3 there. And then we're going to store C there. And then we're going to call F. Now what's going to happen when you call F? Stack frame is pushed for F. It'll have room for Y and D. So whatever the locals are and the parameters. And it'll initialize Y to something and D to something. What does it initialize Y to? All right, we're passing X as the first parameter. So whatever, the code will evaluate the first parameter, which is X, which will be 3. So that becomes initial value of Y, and similarly for D. So that's what it looks like when the method is called. Now the method says Y gets D times D. Y gets Y times Y. What happens? It reads the Y, sees a 3, squares it, stores it back, 9. Then it says D equals the character D, so that changes. Then we return. What happens when you return from a method? Stack frame is popped. And then we're back in here and we change X to 7. All right, so that's just the most basic. There's no heap in this case. We weren't using the heap. There's no new. That's just basic stack. So that's step one. Understand stacks. Okay. Now this is why I said variable names are not stored on the stack. They're not stored in compiled code as long as you're not, if you're compiling in debug mode, then the symbols are kept around to make debugging easier. But in a release version, the variable names aren't there. Instead, fixed offset from the top of the stack are used. So let me explain what I mean. At any point, the stack may have a lot of stack frames in it, but the current method is always using the top stack frame. In this case, it's the only stack frame. So the program knows at all times the address of the first byte at the top of the top stack frame. So imagine it has a pointer here. So in the compiled code, when it says x gets 3, the compiled code says, go to the top of the stack, go down 4 bytes, and store the 3 there. So instead of the variables don't appear in the compiled code, it's offsets. Because when main is running, C will always be at an offset of 0 from the top of the stack. Let's say, okay, and 7 would be at an offset of 2. X would be at an offset of 2 from the top because the character is a 2-byte thing. Okay? So C is stored as an offset of 0, X is stored as an offset of 2. So 0s and 2s show up in the compiled code, but not the symbols. Okay? That's something I've never talked to you about. Okay? So fixed offset. And then the neat thing is, a method may be called many times. Sometimes it may be the 3rd thing on the stack. Sometimes it may be the 10th time or the 100th thing on the stack. But it's always at the top. And there's always a pointer store that knows where the top of the stack is right now. And we could just talk about offsets from that. So this isn't really present. Okay? Now reference types. What's the difference? Now we're talking about the heap. So reference types like arrays, the values are stored on the heap, and then there's a reference stored, in this case from the variable A to the array in memory. So that's what that first statement does. And then we call F with 2 parameters. The array is expecting an array and an integer, so we pass it A and A sub 1. So what's the stack frame going to look like for F when it's pushed? What will be in the stack frame? B and N. What will the value of B be? Be a reference to that. So whatever is stored here, that'll be the value of B. It will be a reference to this. And what will be stored as the value of N? 1. Because the value of A sub I is 1. So we get this picture. So when we say B sub 0 gets 2, that's changing over there. There's a sharing going on. When we say N gets 3, we get that. And again, these guys aren't present. The compile code deals with offsets. So that's the reference type. Now, let's look at reference parameters. This is the same example as before, but we're passing things by reference. So we get set up, we make the call. The stack frame for F will contain Y and D, but what will be stored in Y and D? References back to these addresses. So that when we change Y to Y times Y, we're actually changing X down here. And similarly here, that changes to D. And then that happens. The thing to know is the compiled code knows how to interpret what's stored in that stack frame. So back here. Since it knows that those are reference parameters, it knows to interpret these as addresses as opposed to actual characters or integers. Okay. Here's another example with reference parameters. This is the same as before with the array. So we set up the array. We make the method call. We're going to have B and N up here. What will be stored in those parameters? What will B be? It'll be a green pointer down to here, because we're passing A by reference. What will N contain? Contain a reference to this array element, not to the array element, because that's being passed by reference. So when we say B sub 0 gets 2, what's going to happen?
0 is going to change to 2.
Not, yeah, that's true. What's going to happen when we say N gets 3? That's what I meant to highlight. Yeah, you're doing call by reference, so you don't change this cell, you change the cell it points to. So it changes there. So that's just call by reference in the form I haven't shown you before. Okay? We know structs are value types, and so when you allocate a struct, like main declares an S object, and so we get a struct on the stack, where the M field is here, the N field is there. We set S.N to 5, S. To 7. Again, that'd be done with offsets. Then we call F, and F is expecting one of these structs and also a reference to a struct. So we get that picture. The first parameter is just copied up. The second parameter is a reference to this struct right here. Okay? Then F increments A. Say there's an increment method in the S class. You see it up there. So we're calling method again. We're calling increment. And so the only parameter is this, the object, in this case the struct in which the method was invoked. And so it's passed as a ref parameter to this struct right here. So this is passed as if it were a ref parameter. And then in the case of structs, then when we change, we increment that, we're done. There's the next call to increment. That's incremented. And done. Okay, so that's structs. If you do the same thing with classes, now the object is stored off the stack on the heap. We have a reference from the stack. We set that to 5 and that to 6. We pass them. Again, the first one was passed by value, and so we get a direct arrow to it. The second one was passed by reference, so we get that. Now, we got this, which doesn't have a green arrow now, it just points directly to there, and we call increment twice, and 2 things get incremented, and we gradually return. All right, so we've talked about all that stuff before. This is in new combinations, some of them. But here's something different, method tables. This is talking about inheritance. So I've got a class B up there with 2 virtual methods, and then I've got a class D. One that, in class D, we override F and declare a new virtual method H. So what happens is, for each class, it creates what's called a method table. So that's the method table for B. Okay? So tell me what's included in a method table. What can you gather from that? What's included in a method table? Yeah? Okay, so there's something that identifies the class name in some fashion. That's the second element. What's the first element? What would you imagine that would be?
Reference to the parent object?
Yeah, reference to the superclass method table. So B extends something. If nothing else, it extends objects. So that would be a reference to objects method table. And what's the rest of the method table consist of? The methods. And so you see F, it's going to be the way you get at the code for F, the compiled code for F and G. Okay? So what will the table for D look like? Yeah?
The first element of the table will be class D, I guess. Well, I mean class B, I should say.
Okay, so we'll have a reference to the parent, to the super type, which is D. Then it'll say class D, something identifies the class. And then what? What's the rest of the table going to look like? Well, what did the rest of B's table look like? There was an entry for each method. How many methods are in class D? 3. That's very important. We're inheriting F and overriding it. We're inheriting G. and we're creating age. So you get that picture. Now, this is very important to notice. Class B has F and then G. Class D repeats that, F and then G. So the methods that are shared between these classes are going to occur in the same order. And then the new one comes next. Now, can you imagine why that's important? Notice, this F points to something different than that F, because we overloaded it. G points to the same method as G up there, and H, of course, points to something new. Why is it important that FG, FG occur the same in both places? That the inherited methods occur in the same order, in the same relative location that they occurred in that table up there. Yeah?
Because in the compiled code, it will go to the method table and it'll just look in the known location for whatever
Okay.
it's trying to find.
So to tell you what he said, to understand what he said, you've got to realize that an object actually contains a pointer to the method table. So if you created an object of type B, if you said new B, in addition to having the fields X and Y, it would have a pointer in it to the method table. So that's why you can do, you can test the type of an object at runtime, because it has a pointer to the table, it knows what type it is. Similarly, you have something like that for an object of type Y. Now, when you pass an object, you pass that object to a method that expects an object of type B, and say that method calls the F method. The compiled code is just going to go, it's going to say, okay, to call F, I know I go to the method table, I go to a fixed offset, I expect to find F at a fixed offset from the top of the table, I go to its code, I run it. Now, suppose you pass this to a method that expects an object of type D. Same thing will happen. It'll expect to find, let's say it calls H. It'll expect to find H at a fixed offset in the method table. So the steps in calling the method are, you call the method on this object, you go to its table, you go to a fixed offset to find H, you go to its code. But the key thing that I just asked about is, what happens when you pass this object to a method that expects an object of type B? So a method that expects an object of type B can actually be receiving one of those objects or one of these objects. What's going to happen when you try to call F on it? Yeah?
Look at where F would be in B, and if it's not there in D, then it's going to call whatever's there.
It wants to call F, but the thing to realize is F is stored at the same offset in both tables. So the method we're calling that in turn calls F, it doesn't have to worry, is this an object of type D or B? It just knows to go to the method table, go to the same fixed offset. It doesn't matter what table it is, it'll always be the third one. And then follow the pointer to see which code to call. That's the dynamic dispatch. That's why inheritance has some overhead. It's slower to use, to do overriding, because you got to go through the method table to call. If you have methods that aren't overridable, if they're not virtual, you don't have to store them in the method table. You can just hard code it into the compiled code. It knows what method you're calling. Interfaces are even more complicated. Basically, I'm adding in the method table now, I'm adding a spot that points to a list of interfaces this class implements. So let's say this class implements interfaces I and J. So we've got a pointer to that, I points to J, and each of them points back into here and says, okay, the interface has object G, it goes here, it has methods F and H, they're down here. And so to call a method, you've got to, if you have an object that's being treated as something of type I, you'll have to go here, go find the right interface and find out which method to call, where the method is. So that's even less efficient. So this is just saying non-virtuals are really fast to call. Virtual methods require indirecting through the table. Interfaces require searching through interface tables to find the right one. So that's slow. And you may think what I just did is complicated and inscrutable. That's the actual truth in .NET. This is out of the .NET documentation. This is, you see it says method table. So there's all this information and subsidiary things to make it all work. So what I did is just an abstraction. Yeah?
So are properties stored in the method table as well?
Are properties overridable?
No, are they in the method?
Yeah, but the answer is are properties overridable? And I don't know if they are or not. Can you override a property? If you can, they would have to be stored in the method table. If you can't, they wouldn't need to be. Okay? So we're always using abstraction to simplify our view of the computer. But if you were writing, a C# compiler, you'd have to be intimately familiar with this. Or at least if you're implementing the common language runtime, you have to understand this data structure here, not the one I showed you. But since you're not doing that, my take is good enough. Okay, so for what it's worth, yet another exposure to runtime memory model.